गुड मॉर्निंग डियर फ्रेंड, myself डॉक्टर चंद्रकांत आहेर, MAG कॉलेज मालेगाव काम में आ गया हूँ. So last lecture we start this second chapter, that is calculation using analytical chemistry. We complete this first part, that is some important units and measurement. SI unit, derivative prefixes, conversions, difference between mass and weight, moles, millimoles, calculations and significant figure. So this much part we studied in last lecture. Now we start this second point of this chapter, that is solution and their concentration. The concept of concentration is frequently used as a general term referring to a quantity of substance in a definite volume of solution. So substance quantity in definite volume of solution, that is called as a concentration. So different methods are express the concentration of solution. Chemists use a number of fundamental ways to determine this concentration of solution. These are percent concentration, molar concentration, solution diluent volume ratio, P function. These are the examples of expressing the concentration. See the first, that is a molar concentration. So this molar concentration is one which is prepared by dissolving 1 mole of substance in 1 liter of solution. 1 mole of substance in 1 liter of solution, that is called as a molar concentration of that particular solute, and it is also called as a molarity. So this molar concentration M is equal to number of moles of solute, N small n, divided by volume of solution in liter. Or molar concentration is also expressed as this number of millimoles of solute upon volume of solution in ml, milliliter. The unit of molar concentration is molar, and it is denoted by capital M, expressed as moles per liter or millimoles per liter. For example, this 1 mole solution of oxalic acid means the solution is prepared by dissolving 1 mole of oxalic acid. So what is 1 mole of oxalic acid? So molar mass of oxalic acid. This molar mass of oxalic acid is 126. So we dissolve 126 gram of oxalic acid in 1 liter of solvent. So it gives a 1 molar solution of oxalic acid. The molarity of a solution is always fixed, since this molecular weight of compound does not change. So this is the molar mass of oxalic acid, and thus this is molecular weight is fixed for that particular substance, and thus it is not changed with particular substance, and thus this molar weight of compound does not change. This molar concentration is expressed in two ways: molar analytical concentration and molar equilibrium concentration. This concentration of solute undergo chemical change in solution or not. So these two concentration depends upon the solute concentration in solution, whether it is changed or not. See what is the difference between these two, analytical and equilibrium concentration, molar concentration. So molar analytical concentration. This molar analytical concentration of a solution gives the total number of moles of solute in 1 liter of solution. Total moles of solute in 1 liter of solution, or the total number of millimoles in 1 ml of solution. For example, when we consider the H2SO4 solution has 1 molar concentration. What is that? It is prepared by dissolving 98 gram or 1 mole of H2SO4 in water and make the dilute to 1 liter. So this solution make dilution to 1 liter, and thus this H2SO4 does not undergo any chemical change in water solvent. So this analytical concentration is fixed. What is 1 molar H2SO4 solution? So it have 1 molar of H2SO4 solution in solution. So that is a fixed quantity. But what is a molar equilibrium concentration? This molar equilibrium concentration is expressed in molar concentration of a particular species. Molar concentration of particular species in a solution at equilibrium. So it is at equilibrium position. At equilibrium, what is the condition of that species? That determine this molar equilibrium concentration. It is necessary to know how solute behave when it is dissolved in a particular solvent. How it is dissolved in a particular solvent. So it is, this behavior of solute is important. For example, this molarity of HCl in solution with analytical concentration. We prepare 1 mole HCl solution, that is analytical concentration is 1 molar concentration. That is analytical concentration. But actually it is a 0 molar. How? See, because this HCl is a strong electrolyte. HCl is strong electrolyte, dissociated completely into a mixture of H plus ion and Cl minus ion. Actually, there is no undissociated HCl molecule present in this solution. So when we say 1 molar HCl, so analytical molar concentration is 1 molar. Okay, no problem. We have this 1 molar HCl solution, its analytical concentration is 1 molar. But when we say this molar equilibrium concentration of HCl solution, at that time it is a 0. Why? When we dissolve HCl in water, it dissociated into H plus ion and Cl minus ion. Whatever may be the concentration of HCl which is dissociated into H plus ion and Cl minus ion, and there is a 0 concentration of undissociated HCl. So this undissociated HCl concentration is 0. No HCl is present in undissociated form. All HCl is completely ionized or dissociated. And thus when we say this molar equilibrium concentration of HCl is, it is 0. But analytical concentration is 1 molar, but equilibrium concentration is 0. These equilibrium concentrations are represented by square bracket. So this is a square bracket represent concentration around the chemical formula. Thus this HCl with an analytical concentration is 1 molar, but its equilibrium concentration is 0. Molar equilibrium concentration is 0. See example, calculate the mass of oxalic acid required to prepare 3 liters of 0.5 molar oxalic acid from crystalline oxalic acid. This formula is given. Again this molar mass of crystalline oxalic acid is also given. So how we solve this problem? This total molar moles of oxalic acid in 3 moles of 0.5 molar oxalic acid solution is, so when we consider 1 liter of solution, so it is 0.5 mole, but there is 3 liter, so 3 into 0.5, that is total 1.5 molar oxalic acid is present in 3 liter of solution. So oxalic acid molar concentration is 0.5 mole. So this moles of oxalic acid is 1.5 moles. The mass of oxalic acid to prepare 3 liters of 0.5 molar oxalic acid solution is molar mass 1.5 into, moles of oxalic acid into its molar mass. Molar mass is given 126.07. This multiplication gives the mass of oxalic acid required, that is 189.105 gram. This much mass of oxalic acid when we dissolve in 3 liter of solution, that solution having 0.5 molar oxalic acid solution and volume is 3 liter. For that what we required, this much gram of oxalic acid. Which oxalic acid? Crystalline oxalic acid is used to prepare this solution. Next point is percent concentration. So what is this? Chemist express solution concentration in term of percentage or part per 100. The percent composition of solution can be expressed by many ways as volume percent, that is W by W. This weight of solute in gram upon weight of solution in gram into 100. This percentage gives weight percentage. What is volume percent? Volume to volume. Volume of solution, solute in ml, milliliter. Volume of solution in ml into 100. This percentage gives volume to volume percent. Volume percentage. What is weight to volume percent? W to volume. W to V percent. So this weight of solute in gram and volume of solution in ml into 100. This gives the weight to volume percentage. See in detail. This weight percentage, weight to weight. It is a frequently used in express the concentration of commercially aqueous reagent. These aqueous reagents are commercially supplied in this way. For example, nitric acid sold as a 70% solution. This answer is 70% nitric acid, weight to weight percent. What is the meaning of that? It means that this reagent contains 70 gram nitric acid in 100 gram of solution. 100 gram of solution. In second, volume percentage, It is also frequently used in specific the concentration of solution prepared by dilution of pure liquid. Dilution of pure liquid. So we have the solute in liquid form, we dilute it, we get the solution. Another liquid composition. For example, 5% solution of ethanol. Ethanol is liquid. Its 5% solution means we take this 5 ml of ethanol and we make this volume to 100 ml. See, we dissolve 5 ml of ethanol to make the volume 100 ml. So we make this volume 100 ml. That is the 5% aqueous solution of ethanol. What is weight to volume percentage? W to V. It is often used to indicate the composition of dilute aqueous solution of solid reagent. For example, solid reagent. The solid is solid. For example, 10% silver nitrate, AgNO3, 10%. This final answer is a 10%. What is that 10% silver nitrate? So we take 10 gram of silver nitrate and it dissolve to 100 ml of water solution. So we take 10 gram of silver nitrate and it make volume, dissolve this silver nitrate in 100 ml of water and make this solution. That solution is called as a 10% aqueous solution of silver nitrate, that is weight to volume percent. Next, concentration is expressed in part per million, ppm. So what is this? Part per million, ppm. Solution is one which is prepared by dissolving 1 gram of solute. 1 gram of solute in 10 raised to 6 gram of solution. So this ppm is equal to mass of solute in gram, mass of solvent in grams into 10 raised to 6. Thus this 1 ppm solution is the solution contain 1 gram solute in 10 raised to 6 gram of solution. That means 1 milligram of solute per liter. So 1 milligram per liter of solution. So this 1 gram of solute in 10 raised to 6 gram of solution, that means 1 milligram of solute per liter of solution. For example, 1 milligram per liter of KCl is equivalent to 1 ppm. 1 milligram of KCl is equivalent to 1 ppm of KCl. This method of expressing generally used to express very dilute solutions. Concentration of environmental samples are expressed in ppm, part per million. What is part per billion? Similar to this, only 10 raised to 6. Instead of that we have billion, that is 10 raised to 9. So it is the number of part per billion, 10 raised to 9 per of solution. So formula is mass of solute in gram divided by mass of solution in gram into 10 raised to 9. So it is also defined as 1 ppb, means 1 microgram of solute in 1 liter of solution. In ppm, 1 milligram per liter. In this case 1 ppb, 1 microgram per liter. That is the difference in this two concentration. What is part per thousand? So it is the number of part of solute per thousand, that is 10 raised to 3 or 1000 part of solution. So ppt, part per thousand, mass of solute in gram, mass of solution into 10 raised to 3. It is also expressed as mass of solution in gram upon volume of solution in liter. So that is the part per thousand. Now we consider this example. A 250 ml of aqueous solution contain 55.8 gram of herbicide. Express herbicide concentration in weight to volume percent, part per million and part per billion. So we express this same concentration in 3 different units: volume percent, weight to volume percent, part per, that is ppm, ppb. So what is given? 250 ml of aqueous solution means 0.250 liter. This mass is given, this herbicide mass is 55.8 gram. So this 55.8 gram is 0.0558, sorry, 55.8 milligrams. So that milligram we converted into gram, that is 0.0558 gram. This milligram, when we convert it into microgram, that is gram into 10 raised to gram into 10 raised to 6, that is we get this 55.8 into 10 raised to 3 microgram. 55.8 मिलीग्रॅम म्हणजे 0.0558 ग्रॅम. 55.8 into 10 raised to 3 microgram. So these are the mass but in different unit, fixed mass but different unit, fixed volume but in different unit, ml and liter. Now we calculate these three different unit concentration. First is weight to volume percentage, W to V. So what is formula? Weight of solute in gram and weight of solution in gram. So weight of solute in gram, that is gram, that is this is the quantity gram, 0.0558 gram. Solution in gram, sorry, weight to volume. So this is a ml solution, this is a ml solution. What is ml? 250 ml solution. So this division into 100, we get this 0.02232%. Second, concentration in ppm, weight of solute in milligram. So we take this milligram weight of solute, volume of solution in liter. So liter volume we take, that is 0.25 liter. This ratio gives 223.2 ppm. Next, concentration in ppb, weight of solute in micrograms. We take this microgram weight of solute divided by volume of solution in liter volume. This ratio gives 220. See, this figure is 2,23,200 ppb. See, these concentrations are same but the unit is changed. These figures are same but unit is changed. This is the percent, weight to volume percent, ppm and ppb. So we express this same concentration in three different units of concentration. So that is importance of that concentration. Next point is solute dilute volume ratio. Solution diluent volume ratio. What is solution dilution volume ratio? See, this volume of dilute solution is expressed in terms of volume of more concentration solution. So volume of more concentrated solution and the specific amount of solvent used in diluting it. The ratio of solution shown by putting colon. So what is the meaning of this? In this example, 1:1 HCl. What is this? So we have this HCl solution and we have the concentrated solution of HCl and we have the specific amount of solvent, that is water. So in this case, one part is concentrated HCl solution, this one volume of HCl, and it is double volume of water, that is two part is a water or solvent. So that is 1:1 HCl. So what is solution diluent volume ratio? So 1:1 HCl means one part of concentrated HCl added in two part of water. Next concentration unit is P function. What is P function? This chemist scientists always express the concentration of species in terms of P function or P value. What is P value? So this value is a negative logarithm to the base 10 of molar concentration of that particular species. So that particular species concentration, molar concentration, we take that concentrations negative logarithm to the base 10 of that concentration. That values gives this P value or P function. See this mathematical expression, this P function of x, this x is a species, this P function of x or P value of x is minus log of x concentration to the base 10. This 10 is a logarithmic base 10. The advance of this P values is the allowing concentration that vary over the 10 or more order of magnitude to express the terms of positive number or value. So what is this P function? So it is a negative logarithm to the base 10 of molar concentration of that particular species. So on that we consider this problem. Based on that, calculate the H plus ion concentration. This square bracket represent concentration. H plus ion concentration in the solution that had pH 5.16. So as we know, P function, pH is equal to minus log of H plus ion concentration. This value of pH is 5.16. So when we take this log H plus log of to the, so this log is to the base 10. This log of H plus ion concentration, we shift this negative sign here. This log of H plus ion is equal to minus 5.16. Now this concentration of H plus is calculated as taking the antilog of both sides. So this log is cancelled with antilog. What is remaining? Concentration of H plus ion and this antilog of minus 5.16. When we take this antilog of this figure, we get the concentration of H plus ion, which is equal to 6.9 10 raised to minus 6. So this is the concentration of H plus ion we calculated from P value or P function. Another example, calculate pK for a solution of 2.5 into 10 raised to minus 4 moles of K3PO4. So from this solution, what we calculated? We calculate this potassium ion concentration in terms of P value. So as each moles of K3PO4 contain 3 moles of K plus. So 1 moles of solute gives 3H K plus ion, 3 moles of K plus ion. And thus the concentration of K plus ion is calculated as K plus ion concentration is equal to concentration of K3O potassium phosphate K3PO4 into number of moles, that is 3 moles of K plus multiplied by 3. So this concentration of potassium phosphate is given. When we multiply by 3, we get the concentration of K plus. So this concentration of K plus is 3 times of concentration of potassium phosphate. So value is 7.5 10 raised to minus 4 moles of K plus. Now we calculate this pK. What is pK? Minus log of concentration of K plus ion. In this case, base is 10. So minus log of, we put this value, concentration value 7.5 10 raised to minus 4. We take this, solve this logarithm. What is the pK? 3.12. So this pK value is 3.12. P function of potassium ion is 3.12 for this solution. Then the last point of second topic of this second chapter, that is density and specific gravity of solution. This density is expressed in the mass per unit volume of solution. So density is mass upon volume, that is mass per unit volume of solution. So it is expressed in kilogram per liter. See, kilogram per liter, this K is remaining kilogram per liter or gram per milliliter. Gram per milliliter, this K is missing, kilogram per liter or gram per liter. The specific gravity, the ratio of density of substance to the density of water at 4 degrees centigrade. See, what is specific gravity? The specific gravity is dimensionless and so not used with any system of unit. The numerical value is same as that of density of that substance. So this density of water is approximately 1 gram per ml. So when we consider this specific gravity, it is a density of substance upon density of water. And this ratio, and thus the specific gravity is dimensionless quantity. This molar concentration is also calculated as specific gravity into weight to weight percent of solution into molar concentration upon molar mass. So this formula is used to calculate the molar concentration of solution when specific gravity is given. So the specific gravity is a dimensionless quantity. It is the density of substance upon density of water. So we have this table in which we shown some specific gravity is commonly used acids and bases. So these are the reagent, acids and bases. This concentration is weight to weight percentage and specific gravity, which is dimensionless. This acidic acid 99.7 weight to weight percent, its specific gravity is 1.05. Similar with this ammonia base 29 weight to weight percent, specific gravity is 0.9. Hydrochloric acid HCl 37.2 weight to weight percent, and for that solution specific gravity is 1.19. So similar with nitric acid, sulfuric acid 96.5 weight to weight percent, specific gravity is 1.84%. So this is the specific gravity which is dimensionless. So the third part of this second chapter is chemical stoichiometry, that we have to consider in our third lecture or third video. So this much part we consider for our second topic of second video, second chapter. Thank you very much.